Okay, so good afternoon, everyone. So welcome back to the Chemistry Olympiad training. We'll be doing acids and bases today. So this will be really helpful for us in our Sec 3 Pure Chem as well. So let's jump straight into it. Now let's start with a few definitions and properties. So first things first, from lower sec, actually you have learned what acids are, right? So some acids are commonly found in fruits. For example, oranges contain citric acid, vitamin C is ascorbic acid, vinegar is ethanoic acid. These are common acids found in food. Okay. However, we will need to know the formula of the acids found in the lab. All right. So now we need to memorize the formula of the acids. Hydrochloric acid, HCl. You notice immediately there is H plus and Cl minus formed when it dissociates in water. So if you have done the SLS package on acids and bases, you will know that when you dissolve HCl in water, it dissociates and ionizes in water to give you hydrogen ions, which is H plus. Because it's H plus, the other side will be Cl minus. Similarly, nitric acid will form H plus and NO3 minus when it dissociates and ionizes in water. And this is the reason why the salt form is called a nitrate. When you use nitric acid, the salt is a nitrate. And the reason is because it forms the nitrate ion. All right. I'm sure you can continue. You can imagine H2SO4 will form H plus and the sulfate ion. So later on, we will write equations to show this, and so on and so forth. Now, these 5 formula must be learned. You will need to be able to write this formula from memory because there is no way to deduce them from the periodic table alone. All right. So let's take this time to actually learn the formula of hydrochloric acid, nitric acid, sulfuric acid, phosphoric acid, and finally, ethanoic acid. Some common properties of acids that you have learned in Sec 2 include they have a sour taste, they taste sour. That's why sour fruits generally will contain a lot of acids. They turn blue litmus paper red, but perhaps let's add one more word. They turn moist blue litmus paper red. The litmus paper has to be moistened with some water before you start. Acids also dissolve in water to form solutions which can conduct electricity. We'll see why later on. And today, we will finish all 3 reactions of acids and learn how to balance equations. All right? So this is the equivalent of, say, 3 lessons into 1 lesson today. Now, if you just look at all the formula that have been highlighted in yellow, all the formula of the acids, you will notice something in common about the chemical formula. I'm sure you have spotted it. All of them contain hydrogen. There is hydrogen in all the formula of the acids. All right. Of course, this is central to actually the function of the acid. So now let's move on to the definition of acids at upper sec. So an acid is actually a chemical substance. It's a chemical that dissociates and ionizes to give hydrogen ion. Hydrogen ion is called H plus ions in an aqueous solution. All right. Now let's try to break down these words, dissociate and ionize. The easier word to actually dissect is dissociate and ionize, right? Dissociate is harder, ionize is easier. Ionize means to form ions. So it forms H plus. It becomes charged. Originally, it's not charged. Now it became charged, H plus, right? Now, the word dissociate is a very scientific way of putting the concept of it broke up. So, for instance, HCl. Now, HCl is a simple covalent molecular structure. So, HCl is a covalent molecule where the H and the Cl originally had shared electrons with one another. So please don't be mistaken. HCl is not ionic. It's covalent. But when it dissolves in water, what happens is the shared electrons will migrate to chlorine. When you dissolve it in water, the water molecules start interacting with the HCl. When the water molecules interact with the HCl, the shared electrons, which I've highlighted in yellow, will migrate and go over to the chlorine entirely. Now, this makes sense now that you have learned electronegativity. Chlorine is more electronegative than hydrogen. Therefore, it attracts the electrons over more readily. The shared electrons will be attracted to chlorine more. So it's natural that once you dissolve in water, right, you add water in, what happens is the electrons go entirely to chlorine. If the electrons go entirely to chlorine, effectively, chlorine gain hydrogen's electrons. Chlorine gain the one electron from hydrogen. Chlorine gain electrons, so minus. Hydrogen effectively lost its electron to chlorine, plus. All right? So the idea is an originally covalent molecule, HCl, where there's sharing of the electrons, now no longer has sharing, and this is because you have added water in. You dissolved it in water. The water molecule causes the shared electrons to essentially go over to chlorine entirely. How does this work? Of course, this also works because water itself is a polar covalent molecule, right? So we spoke about this when we talked about polar covalent bonds, electronegativity, and that's how you appreciate. Oh, so that's why electronegativity is important. It allows me to predict how will the shared electrons move. In this case, they move to chlorine, which is much more electronegative than hydrogen. All right, so the idea is, in order for the dissociation to happen, you need water. You need to dissolve in water. Dissolve in water is called aqueous. So when we say something is aqueous, we don't mean it's a liquid. It's not the same. Aqueous is not the same as liquid. Aqueous means you added water to dissolve it. It's a solution. Liquid means you have melted it. So we always say aqueous sodium chloride. You dissolve sodium chloride in water. You will not say liquid sodium chloride. Liquid sodium chloride literally means you took the salt, sodium chloride, you heated up until a very high temperature, then it melted. It's not the same concept. All right? Now, so this brings us to the time to think below. Is HCl gas considered an acid? Obviously, a gas means it's not dissolved in water, right? It's just a gas. So the answer is HCl gas is not an acid. Shockingly, HCl gas is actually neutral. If you were to put in blue litmus paper, it wouldn't change color. Because water is needed for the two processes. What are the two processes? Dissociation and ionization. You need water to be present for dissociation to break up, ionization to form ions with charge of acids to produce H plus ions. Okay, without water, if it's totally dry, it will not be acidic at all. And this also explains why when you want to use litmus paper to test for an acid, you need to moisten the litmus paper. The moisture, which is water, basically provides the water needed for dissociation and ionization of the acids. If it's perfectly dry, you wouldn't see acidic properties. And this leads us to the final conclusion. H plus ions are responsible for acidic properties. That means if the acid can react with carbonate, acid can react with metal, it's because the acid has H plus ions. All right? So at this juncture, let me pause for a short while to see if you have any questions that you wish to ask. All right? Okay, reminder, you can use the Q&A function now, which you can find in the activities bar. All right. And it allows you to ask questions through the Q&A, which I can see. Okay. Okay, if not, I'll move on. Now, important terms to describe acids. There are two important terms. The first term is basicity, which has to do with how many H plus do you get from one molecule of the acid. You notice for HCl and HNO3, you get one H plus per molecule of HCl dissociated. That's obvious because HCl only has one H anyway. The difficulty comes in when you have sulfuric acid. Sulfuric acid is H2SO4. And the biggest mistake that many students make is that they say, oh, because it's H2SO4, therefore it's H2 plus. No, it doesn't work that way. What happens is sulfuric acid produces 2H plus. 2H plus is not equals to H2 plus. They are not the same things. How are they not the same thing? Obviously, the placement of the two makes a huge difference. So let's look at what's 2H plus. When the 2 is in front, what it means is you have double the amount of H plus. 1H plus, 2H plus. Double the amount. 2 times the amount of H plus. It's a consideration of the amount. Whereas if you have written H2 plus, the 2 is at the bottom, it means like this. The two hydrogens are bonded to each other. And somehow the whole thing has a positive charge. So when you write the 2 at the bottom, it means it's bonded together. And of course, that's not the case for sulfuric acid. For sulfuric acid, you just learn acids dissociate. They need to break up. So the H plus should not be bonding to each other. What we mean to say is that it produces double the amount of H plus. But once formed, the H plus are not bonded to each other, right? In fact, why should H plus bond to each other? They are both positively charged. They should repel each other, if anything at all. So definitely, 2H plus is the correct version. Double the amount of H plus. It's never going to be H2 plus. All right? So sulfuric acid has 2 times the amount of H plus, therefore it's dibasic. It produces 2H plus per molecule of sulfuric acid. Finally, phosphoric acid, H3PO4, 3H plus, tribasic. Okay? Now, the next concept is the strength of acids, which is the main concept for today. Acids can be considered either strong or weak. There is a big difference. All right? This is a very important concept. A strong acid dissociates and ionizes completely and irreversibly when dissolved in water. The dissociation of a strong acid is complete and it's not reversible. If you just use nitric acid as an example, look at the arrow. The arrow is one direction, from left to right. That's it. Right? From HNO3 to H plus. It's not going to reverse backwards. It's irreversible and it's complete. Complete means if I have 100 molecules of HNO3, all 100 will dissociate to form H plus when dissolved in water. Okay? As a result, strong acids tend to have a higher concentration of H plus. If they have a higher concentration of H plus, the pH is lower. We will see the formula for pH later. Higher H plus concentration actually causes the pH to decrease. Next, weak acids, on the other hand, dissociate partially and reversibly. Now you can see this in the dissociation of ethanoic acid. Ethanoic acid dissociates reversibly. It's quite obvious based on the arrow. look at the arrow, the difference in the arrows. The arrow for dissociation of ethanoic acid is two directional. It goes left to right. It also goes backwards, right to left. So this tells you that it's reversible. Once formed, the H plus could very well combine with the other anion to go backwards. All right, so it's reversible. Now, what is the meaning of partial? Partial means out of 100 molecules of ethanoic acid dissolved in water, perhaps only one molecule out of 100 molecules will form H plus. All right. Now, this is a property of weak acids. Now, in this case, ethanoic acid. Ethanoic acid is found in vinegar. It's the main component of vinegar. Vinegar is basically ethanoic acid and some water, if you like. Now, because it's dissolved in water, it forms H plus ions. Okay. Now, how can you tell from this equation it's dissolved in water? You have the state symbols. AQ, AQ, AQ. Now, this AQ is called a state symbol. State symbol. It is always put after the formula of the substance in brackets. All right. So we put it after the formula. Now, we cannot be writing aqueous, aqueous, and spelling out so many times, right? So we need a quick way. So we give it symbols. AQ, obviously, stands for aqueous, which is dissolved in water, right? So that's one possible state, very common in chemistry. Most of the things we do are dissolved in water, aqueous. Of course, the other three states of matter you should know. The three states of matter are solid, liquid, and finally, gas. So, of course, we are not going to write solid sodium carbonate. We are going to write sodium carbonate bracket S, right? It's faster. So, solid, liquid, gas, SLG. So, add one more to your dictionary now. AQ. AQ is aqueous or dissolved in water. Okay? Now, we started with ethanoic acid. We are ending off with H plus, hydrogen ions. And you have this thing here, CH3COO minus. Now, CH3COO minus is called ethanoate. So you notice, right? The name of the anion will somehow follow the acid. The acid is called ethanoic acid, therefore ethanoate ion. If it's nitric acid, nitrate ion. Sulfuric acid, sulfate ion, which is why learning the names of the ions and their formula is so crucial. Okay, so now we're going to focus on strength of acids for the next 15 minutes or so. We are now going to move on to the A-level components. All right, we're going to move on to the A-level component right now to discuss strength of acids using a mathematical manner. So let's move on to the mathematics of this. Don't worry, it's not difficult. You just need standard form. Now, how do you mathematically express the strength of an acid? Obviously, that's important, right? We can't possibly just say, oh, this acid is strong, that acid is weak. Perhaps you want to put it in numbers. So let's assume the acid is HA. A can be anything. All right. We know by now acids dissociate and ionize to form H plus. That means A must be minus when dissolved in water. So HA becomes H plus and A minus. So let's express this as a fraction. Let's express the concentration of H plus times the concentration of A minus over the concentration of HA. Basically, what Mr. So is doing, product over reactant. I'm taking how much product is formed in terms of concentrations over how much reactant is left. Product over reactant. So you learn in Sec 2 when you first learn chemical changes. In every reaction, there's a product, there's a reactant. Product is what you form at the end, which is on the right-hand side. So in this case, H plus is a product, A minus is a product, whereas HA was a reactant. So you got to ask yourself, if the acid is strong, you just learn strong acids dissociate completely and irreversibly. If the dissociation is complete, it means at the end, everything is H plus. There is very, very little HA left. Keyword here is left behind. There should be very, very little HA undissociated if it's a strong acid. Strong acid dissociate completely. So HA at the end should be close to zero, right? So you think it's a fraction. If the denominator, the reactant left is so little, like zero, then your value will be very big because you are dividing by a very small number. So a higher value for Ka tells you it's a stronger acid. Why? Because there's a greater extent of dissociation. It dissociated more completely. All right. On the other hand, a lower Ka value indicates a weaker acid because it dissociated less to a lesser extent. And now we can find these Ka values online. You just have to basically type into online portal like Google. You will be able to get the Ka values very, very quickly. Immediately you notice they are always given in standard form. For instance, I've given you 4 different acids here. The Ka is given in standard form. So for standard form, the first thing you need to look at is the power. Power 10 to the power of what, right? So immediately you can see, amongst the 4 acids in the table, HF to HI, what can you say? As you go down, by the way, F, Cl, Br, and I, they are in the same group. This is group 17. As we go down group 17, does the acid become stronger or does it become weaker? I think you can quite clearly see. As you go down the group, the Ka becomes larger. The Ka increases. From the power of 10, you can see that 10 to the power minus 4, then 10 to the power 6, 10 to the power 9. The Ka increases. If Ka becomes higher, the acid becomes stronger. Okay? So it's quite clear. As we go down group 17, the acids, they form with hydrogen. So HCl, HBr, Hi. HBr should be stronger than HCl. HCl is stronger than HF. It's proven. Next, let me bring up another data point. The other data point is called bond energy. So if you have done the previous set of Chem O training, bond energy is basically the energy needed to overcome the covalent bond. So in this case, I'm taking the energy needed to actually separate the atoms by breaking the covalent bond. So you can clearly see, as you go down the group, from F to Cl to Br to I, as you go down group 17, the bond energy decreases, right? So what does it mean? If bond energy decrease, you need less energy to dissociate or separate Hi, right? To separate them, you need to overcome the covalent bond. Because you need less energy to dissociate H and I, it dissociates more readily, more completely. Therefore, the acid is stronger. So this is the linkage between the two concepts. Because the covalent bond requires less energy to break or overcome, therefore, it's easier to dissociate H and I. Therefore, it dissociates more completely. The acid Hi is stronger. All right? So I hope you can see these trends and link them accordingly. So at this juncture, again, I shall pause for some questions. You can go to the Q&A and type. Okay, there was a Q&A question about SLS. Later, I'll answer that. But any questions about strength of acids first? If you're okay, perhaps you can also give me a reaction so that I know that you're fine. Okay, so importantly in chemistry, let's also learn to make some of these linkages. So as you write your notes, can I please also advise all of us, when you write down the notes, make these linkages, connections. Okay, don't just write it out in sentences. Make sure you link here and there. And as you reread the notes later, do also internalize these connections through reflection, through asking yourself, hey, how is this property linked to the other one property? Okay. So now we're going to move on and look at more strength in acids. We're going to look at more Kas. Basically, I pulled out different acids. All right. And I gave you the Ka. So over here, obviously, the difference is how many carbons it had. Quite clearly, the first one has 1 carbon. The second one has 2 carbons. This one has 3 carbons. Now they have names. 1 carbon. The 1 carbon acid is called methanoic acid. Meth means there is 1 carbon. Okay, so this is organic chemistry. This is how we name things in organic chemistry. All right, so I'll go to organic chemistry later, but just take note. 1 carbon is called meth. If there are 2 carbons in total, we call it eth. So ethanoic acid has 2 carbons. If there are 3 carbons, we will call it prop. So propanoic acid has 3 carbons. So essentially, to indicate the number of carbons, we change the first part of the name, the prefix. Okay, meth, eth, prop. So you can clearly see, as the number of carbon increases, the chain length increases in length. It must, right? There are more atoms. So as you have more atoms of carbon, what happens to Ka? So we can take a look. Again, focus on the power, please. At first, it's 10 to the power -4, then -5, -5. You can see the value next, 1.74, 1.35. So you can see that Ka decreases. As the chain length increases, as the number of carbon increase, the Ka decrease. You can see that. So if Ka decrease, the acid is weaker. All right, the acid becomes weaker if the chain length increases due to increase in number of carbon atoms. So these are trends that you must see. All right, so this is the relationship between the chain length of carbon and the corresponding strength of the acid formed. Okay, so that's to do with chain length. The next one, which is on the next page, deals with what happens if you attach electronegative atoms to the acid. So moving on. At first, it's all hydrogens. What if I suddenly introduced a chlorine on the adjacent carbon atom? You might think that there's no real impact, right? It's on the adjacent carbon. But the wonders of chemistry tells you there is an impact, because the Ka has immediately become 10 to the power of -3. Okay, so you can clearly see the Ka increased. Right? When you substituted the hydrogen for chlorine, the Ka increased, and it's increasing by 100 times. 10 to the power of -5 to 10 to the power of -3 is 100 times increase, actually. But we don't stop there. What if instead of chlorine, I put a fluorine at the same spot? Again, Ka increased about 1.5 times. All right? So why? So hopefully you remember from the previous lecture, fluorine is the most electronegative. It's a very, very, very electronegative element, right? So if there are electronegative elements, we can conclude Ka increase. So electronegative atoms cause Ka to increase. If Ka increase, it's a stronger acid. Okay, now the reason for this, we cannot go into it now. We can go into it later when we discuss a little bit more okay, perhaps in our pure chem lessons. But for now, what's important is for us to read the data and to get the trend. The explanation for the trend, let's leave it, all right, until later on when we do more chemistry. So if you have electronegative atoms, it increases the Ka and makes it stronger an acid. So of course, what happens if I substituted all the hydrogens with fluorines? I'm sure you can imagine the Ka will be larger or higher than if there was only one fluorine. So it'll be higher than 2.19 times 10 to the power negative 3. Okay? It's much stronger in acid. All right? So this brings us to the end of this concept of strength of acids. We are now going to be moving on to the reactions of acids. I will be going through them quickly. Okay, last lesson, during our pure chem lesson, we have also gone through how to balance equations as an introduction. So let's just recap a little bit on how to balance equations, all right? Okay, so if we are ready, let's move on to the next page. Reactions of acids. So acid plus metal is the first one. Acid plus metal becomes salt and hydrogen gas. Okay, so please remember all the gens, hydrogen, oxygen, nitrogen gas. It will be H2 gas. All right. Why H2? We have done this in covalent bonding. The hydrogen atom has one electron. It's not a fully filled outermost shell. So it will share an electron with another hydrogen atom to form the H2 covalent molecule. So hydrogen gas basically contains the covalent molecule H2. We will need to reflect that in our equation. It is not correct to say hydrogen gas is H. Hydrogen gas will never be H because H does not have a fully filled outermost shell. Remember, the aim is for the atoms to bond such that they achieve a fully filled outermost shell. For hydrogen gas, that just means two atoms of hydrogen share electrons with one another to form the H2 molecule. So all the gens, hydrogen, oxygen, nitrogen, gas. Whenever we say nitrogen gas, oxygen gas, we mean the diatomic molecule, H2O2, N2. Okay, so I've said so much. Let's do an example. Calcium. Now, calcium metal is an element. The metal is an element. The element will have no charge at the start. So at the start, it cannot be Ca2+. It's an element. It's not combined yet. It will only have the charge after it lost electron to someone else. But at the start, it's an element. The metal is an element. So just Ca. Hydrochloric acid, we will need to memorize, is HCl. Calcium chloride is where you need to think of charge. It's combined. Calcium with Cl. Ca with Cl. May I know what's the charge? 2 plus, 1 minus. Therefore, CaCl 2. Then we have H2, hydrogen. Gen, 2, 2, 2. Okay, please remember that. Then we just have to finish by balancing the equation by putting numbers as coefficients in front of the acid. Why is there 2 in front of the HCl? Because I have 2 chlorines on the right-hand side. I will need to multiply the 2 to the HCl to balance out and ensure the left-hand side also has 2 Cls. Let's visualize what 2 HCl means. 2 HCl means this. 1 HCl, 2 HCl, basically 2 times the amount of HCl. Okay? So whenever you want to balance an equation, you will have to put a number in front as a coefficient. Okay? So let's revise. In order to balance the equation, you must first write the formula correctly, meaning you will need to write CaCl2 correctly, H2 correctly. When writing formula, that's when the 2 goes below. Once you have written the formula correctly, the next step is to consider, are the numbers of atoms on both sides, left and right, the same? In the case of this equation, it was not the same because on the left, there was only 1 Cl. On the right, there's 2 Cls. Therefore, on the left, there was a deficiency. When you have a deficiency, you need to multiply it by a number. In this case, we need to achieve 2 Cls. Therefore, multiply 2. When you multiply, you will put the number in front, 2 HCl. All right. Now, this is an important concept in balancing equations. So, may I encourage all of us to finish quick check 2. Okay. Now, I'm going to spend a little bit of time on this before giving you the answer. So, please do it now. Do both filling in the blanks as well as the chemical equation and balance the chemical equation. Please start now. May I just give you about 3 minutes to do it before I review the answers? Okay. Okay. At the same time, if you have questions, like I said, do ask it in the Q&A portion of the meeting. Okay, perhaps I'll give you 1 more minute to complete the equations to the best of your ability. As you can see, your speed in writing the equations depends very much on whether you are able to write the formula correctly. So if you were able to write zinc nitrate within 10 seconds, you will finish the entire equation in 30 seconds at most. All right. So it's very important to write formula correctly now. Okay, so I hope you have had a start. You have made a start. You have deduced the names of the missing salt. So it's zinc nitrate for A, beryllium sulfate for B, and finally for C is magnesium nitrate. Those were the names of the missing salts. And now I shall write the equation quick. Now for the equations I'm going to write, I would also have included state symbol as a start. All right. So now let me show you the equations. All right. So you can see the zinc solid. Metals are solids mostly, right? Acids must always be aqueous. Without water, they will not be able.
Nitric acid, yeah.
Okay, without water, they will not be able to dissociate and ionize. All right, so acids must always be aqueous. The salt is aqueous. All right, and finally, hydrogen is a gas, hydrogen gas. Next, beryllium. Beryllium is also a solid. Sulfuric acid is H2SO4 aqueous. Beryllium sulfate is BeSO4 aqueous plus H2 gas. Finally, magnesium plus nitric acid. Now, you must be wondering, how did I write so quickly? course, I've done this many, many times. But beyond that, another good trick to learn is whenever you have nitrates, the NO3 does not split up. Meaning, if you have two nitrates, let's say it's zinc nitrate, Zn bracket NO32, if you have two nitrates on the right, you must have two HNO3 because one HNO3 only has one nitrate. You need two of it. All right. So the NO3 will not split up and break up in a reaction typically. All right. Now, so if we look at all these reactions, you would immediately realize what the metal is doing is actually, the metal is actually displacing hydrogen. The metal is displacing hydrogen from the acid. The word displace means to kick out. All right, to kick out. Basically, at first, hydrogen was together with, let's say, nitrate. They were together. HNO3, they are bonded together. But now, the metal is basically displacing the hydrogen from the acid. Can all metals do this though? Magnesium and zinc clearly can. But do all metals do this? It depends on the reactivity of the metal. And this is where we come to the concept of reactivity series of metals, which we will do this in term 3 for pure chem. Now, metals don't all have the same reactivity. Some metals are super reactive and explosive. They explode, they ignite. Some metals, they are so unreactive, they stay there forever. They are everlasting. So now we shall write down the reactivity series of metals. I'm using their chemical symbols. Hopefully, you can recognize their chemical symbols. Okay, there's a dot, dot, dot. Use a dotted line to put carbon there. Dot, dot, dot. Put a dotted line again to put hydrogen there. Okay, some of these metals you may never have heard of before, right? So these chemical symbols may be unfamiliar to you, but it's fine. Let's just write it down first. Okay, and I'll explain why we use dotted lines for carbon and hydrogen later. Okay, so of course, you must know the names of these metals. For example, the metal that has the symbol K is potassium, Na is sodium, and so on and so forth. All right. Now, the series is written vertically, right, from top to bottom. That's because the top is the most reactive metal. That means amongst this series of metals, potassium has the highest reactivity. Whereas PT right at the end, PT is a metal called platinum. Platinum is the least reactive metal. Okay, you may not know platinum, but hopefully you will know AU. AU, which is above platinum, second last in the series. AU is gold. Gold metal. AG is silver. All right. AG is silver. So you notice gold, silver, platinum. Platinum maybe you have heard of before as well. Gold, silver, and platinum, they are super unreactive. They are right at the bottom. All right, super duper unreactive. They are right at the bottom. And the way to remember them is to remember what gold and silver and platinum are used for. Gold, silver, and platinum, they are commonly used to make jewelry. In particular, wedding rings. Wedding rings will never be made of zinc. All right. The way to tell whether the ring is made of gold or silver is look at the price, of course. So you notice if you go online shopping, like Shopee, you will notice that rings can be as cheap as like $5, $6. Those rings are definitely made of zinc alloy. they won't be made of silver and gold. Silver and gold is much more expensive. Why are they much more expensive? Because silver and gold are rare. But beyond that, wedding rings which are made of gold have a special meaning to them. Because gold is so unreactive, it doesn't react with water, doesn't react with acid, doesn't react with oxygen, basically doesn't react. Okay? That signifies that the love in the marriage will be everlasting. It won't change. And that's why wedding rings are made of gold or platinum increasingly, okay? So if you have heard of wedding rings made of white gold is actually platinum, okay, or platinum alloyed with some gold, okay? Now, why did I use dotted line? It's deliberate. I used dotted lines and I didn't put the carbon directly inside. It's because clearly carbon is not a metal. Clearly, hydrogen is also not a metal. It's not shiny, it's not silvery, it doesn't conduct electricity, right? Hydrogen. Okay? But we still insert them into the series because it tells us something important. Only the metals above hydrogen, can displace hydrogen from acid. Which means only the metals which are above hydrogen could react with acids. Not all metals can react with acid. Okay, so potassium, of course, it can react with acid. All right, zinc can, because it's above hydrogen. However, copper, silver, gold, and platinum will have no reaction whatsoever with acids because they are below hydrogen in the reactivity series of metals. All right. So, of course, do students need to memorize the reactivity series? The answer is yes. You will need to memorize this list of metals. That's why I wrote it out just now. All right. But take some time to do it. Okay. It's not urgent. What's more important is that you need to have the concept that not all metals can react with acid. Those that do react, it is simply because they are above hydrogen, so they can displace hydrogen from the acid. All right. Now, we only inserted carbon and hydrogen. We will not insert other non-metals into this series. All right? Because there must be a reason why we inserted these elements in, right? So in this case, I've spoken about hydrogen. Hydrogen tells us, okay, whether the metal could react with the acid or is it unreactive with the acid. So copper, silver, gold, they don't react with acids. Okay, so that was acid plus metal. I've spoken quite long. All right, if you have done the SLS, you will know that it produces hydrogen gas. I hope we remember what's the test for hydrogen gas. If you don't remember, please go back to the SLS, all right? We need to move on to the next reaction. The next reaction is acid plus base. Acid plus base forms salt and water. Now, in Sec 2, you learn acid plus alkali, right? But at upper sec, we will say acid plus base. So it's acid plus base. Base, what is base? Base is a metal oxide or a metal hydroxide. There's only one exception to this. Ammonia is also a base. All right, so a base is a metal oxide or a metal hydroxide. Okay? So base is either a metal oxide or metal hydroxide. Then what is alkali? Alkali must dissolve in water. Not all metal oxides and hydroxides can dissolve in water. Some don't. For example, zinc oxide. Zinc oxide is insoluble in water. So actually, zinc oxide doesn't dissolve in water. So zinc oxide is not an alkali, but it's a base. Okay? So that's an example. Now, we will take this slowly. You will see which ones can dissolve, which ones cannot dissolve. I will go through slowly with you in class. But what's more important again is to write the equations. So again, I'm going to go through quickly with you. Example 2 and example 3. Example 2, sodium hydroxide plus nitric acid. sodium hydroxide, nitric acid. So I hope you remember from Sec 2, your salt's name must include the metal. It must also come with something from the acid. So sodium nitrate is the salt's name. All right, because the metal here is sodium. Now, it's sodium hydroxide plus nitric acid. So this is neutralization because it produces salt, which is neutral, pH 7, water, pH 7. So let's not forget the water as a product. Now we need to write the chemical equation. Sodium hydroxide is NaOH. Good to remember. Aqueous. Nitric acid, HNO3, aqueous. Arrow, it forms sodium nitrate, NaNO3 aqueous plus H2O. Now, H2O is not aqueous. Water doesn't dissolve in water. It's rather odd to say water dissolves in water, right? H2O is a liquid. Okay? So this is a convention. We would say that H2O is liquid. We don't say H2O aqueous. Now, if you just look at this equation, the formula is correctly written, right? HNO3, NaNO3. These are correct formula. Once the formula are correct, we need to balance the equation. Balancing the equation means ensuring the number of atoms on both sides is the same. If you count it now, it's the same. All right? It's perfectly balanced. There's one Na on both sides, there's one nitrate on both sides, and so on and so forth. So this is perfectly balanced. So there's no need to multiply other numbers to it. Next one, aqueous ammonia plus hydrochloric acid. Before we even get to the words, let's try to write the chemical equation. Ammonia is NH3. You must memorize this from covalent bonding. NH3 aqueous plus HCl aqueous. Aqueous ammonia, hydrochloric acid is also aqueous. It's quite obvious. How would you write H2O? There's no O, right, in this equation. So the product is just ammonium chloride. NH4Cl, ammonium chloride. And then you must be wondering, so is it not going to be neutralization? I thought neutralization must have salt and water. Yeah, there is water formed. There is water formed. But why is it that it doesn't show up in the equation? It doesn't show up in the equation because aqueous ammonia requires water for dissociation. There is no oxygen in the formula of aqueous ammonia. That means I needed to add H2O on the left. I need to put in H2O for it to dissociate first. Then it produces water at the end. It's like I actually use up $1 for my work, but my work produced $1. So I use up $1, I produce $1. So overall, the H2O will cancel out. I use up one H2O at the start for dissociation of the ammonia, and then I produce one H2O at the end. And therefore, you do not see the ammonia, the water, whenever you write the equation for ammonia. So whenever you have aqueous ammonia, the chemical equation will not have H2O on the right. All right? Whenever you use aqueous ammonia, the chemical equation will not have H2O produced at the end on the right. The reason is because for aqueous ammonia and H3, implicit in this formula is that you need to add H2O in at the start and H2O is produced at the end. So it cancels out. All right? So it cancels out. That's why you don't see it. All right? But in reality, it does produce water. It's just that is offset. It's cancelled out by the H2O needed at the start to dissociate the ammonia. Now, in some of the older worksheets or the older textbooks, you may hear instead of aqueous ammonia, they say ammonium hydroxide. In fact, okay, I think we used to teach students ammonium hydroxide instead of aqueous ammonia to help the students. But it's not helpful because for the exam, they will never say ammonium hydroxide. They will write aqueous ammonia. So you need to know aqueous ammonia is NH3 aqueous. Aqueous ammonia will not have H2O in the chemical equation at the end. And that's because it's cancelled out by the H2O at the start. All right. Now, quick check 3, you will need to do it yourself. Okay. Can I just get you to do 1A though? Let's just do 1A. All right. Let's just do 1A quickly before we move on. Okay. Okay, try to think what's the formula of potassium hydroxide, what's the formula of sulfuric acid, what is the salt formed. All right. Okay, so again, I hope you have realized it's acid plus alkali. There's an acid and there's an alkali, hydroxide. Hydroxide is a base or an alkali, right? Okay, so let's start. Because it's acid plus alkali, it's neutralization. It produces salt and water. Okay, the salt is called potassium sulfate because the metal here is potassium. The sulfate comes from the sulfuric acid. Sulfuric acid, final product, sulfate. If you're having difficulties with figuring out the names of the salt, let's try to revise using the SLS. Let's also try to practice a number of things, okay? So one of my Sec 2s is here. So my Sec 2 class has practiced this like countless times, all right? Okay, so let's practice this. So potassium hydroxide is KOH. We know that because group 1, potassium. Group 1, lose 1 valence electron, so it's K plus charge. OH minus, so KOH. Okay, this is aqueous. Sulfuric acid, must memorize formula, H2SO4 aqueous. And there we come to potassium sulfate. Potassium is group 1, so it forms K plus. Sulfate is SO4 with a 2 minus charge. Hence, the formula is not KSO4. It's not KSO4. It's K2SO4. Aqueous plus H2O liquid. Remember, water is a liquid. It's not aqueous. You need to write the formula correctly first. Then we balance. Balance means look at the numbers of atoms on both sides. It's immediately clear you must start counting from the metal. There is a different number of potassium on the left and right. On the right, there is K2, that's 2 potassiums. However, on the left, there is only 1 potassium in KOH. Therefore, you need 2 times the amount of KOH. This ensures you have 2 potassiums on the left and right. After that, you will count the sulfates. Make sure the sulfate is balanced. 1 sulfate, 1 sulfate. Lastly, and this is the trick that I want to show you. To balance more quickly, if there is 2 KOH, that means you have 2 K, 2 potassiums. But the 2 doesn't stop at just the potassium. The 2 is in front. It's like expansion in algebra. If you put the 2 in front, it applies to everything in that group, in that package. 2 KOH means it has 2K. It also has 2 OH. Whenever you have 2 OH, you will have 2 H2O. The number of H2O in the balanced equation is equals to the number of OH minus. If you had 2 OH minus, in this case, you must have 2 H2O. I can give you the answer for part C very quickly. Part C is iron 3 hydroxide. The reason why I can give you the answer quickly is simply because Okay, I've not put in state symbols. Okay, let's just not put in state symbols for now. I know I need 3 HNO3 because there are 3 nitrates. There's 3 OH in the formula on its own, therefore 3 H2O. All right, so the answer for part C is really fast. Once you know how to balance the equation and the trick that the number of water on the right hand side is equals to the number of OH minus, you will be able to balance fast without having to count so many times. Okay, now I'm mindful of the time. All right, so may I encourage you to do quick check 3, and also, all right, if you have done the SLS, you would have done acid plus carbonate as well, right? So acid plus carbonate is the next reaction, which will be covered on page 11 and 12, for which there's a ton of questions that to be done. So can I please assign quick check 3 for you to do as homework, do everything? The next one, do the carbonate examples yourself, try it yourself. Also do quick check for all of it yourself. This is basic practice that you need to go through in order to ensure you are able to cope with the balancing of equations. Now, Mr. So is just going to quickly move on to page 13. All right, page 13. So let's move on in the last 10 minutes to bases and alkalis. So just now we just said what is a base. A base, this is page 13, by the way. A base is a metal oxide, so zinc oxide, magnesium oxide, calcium oxide, metal oxide, or a metal hydroxide. For instance, calcium hydroxide, sodium hydroxide. Okay, these are all bases. So it's defined as a metal oxide or hydroxide that reacts with an acid to produce only salt and water. This reaction is, of course, called neutralization. All right, so this is how bases are defined. Okay, the only exception is ammonia. Okay, why is ammonia so unique and special? Let's get to the bottom of it. Now, ammonia is very problematic because there is no oxygen in its formula. Ammonia, however, once it meets water, it is able to dissociate and ionize in water to form OH minus ions. And this brings us to the next term, alkali. An alkali is actually a soluble base. That means a base that can dissolve in water to dissociate and ionize when dissolved in water to give hydroxide ions, OH minus. So you can see, alkalis are more restrictive. They must give hydroxide ions. They must dissolve in water. All right. Ammonia falls under this category because it's able to dissolve in water to form hydroxide ions. And you can clearly see hydroxide, OH minus, right? Ammonia plus H2O forms OH minus. But more importantly, you can also see ammonium there. NH4 plus, ammonium. That's why ammonia, the salt form is ammonium, because it forms NH4 plus when you add H2O to ammonia. And that's why you can see why in the past, especially when I was a student, I learned ammonium hydroxide. Okay, because ammonia dissolved in water effectively forms ammonium hydroxide. But why don't call it ammonium hydroxide anymore? The reason is because of this arrow. If you look at ammonia's dissociation, there is again this arrow, which is 2 direction. So if you recall, the 2-directional arrow indicates reversible. It goes forward, it can go backwards. Reversible. And what did we learn about reversible? Just now, acids, you learned. If the acid is strong, it dissociates and ionizes completely and irreversibly. However, if the acid is weak, it dissociates partially and reversibly. So reversible means it's weak. So what is this? It's not a weak acid because it produces OH minus. OH minus hydroxide is a weak alkali. So ammonia is an example of a weak alkali, whereas sodium hydroxide clearly is a strong alkali. You can tell it's a strong alkali because sodium hydroxide dissociates and ionizes completely and irreversibly when dissolved in water. The arrows are completely different. All right. So alkalis also have strength. Sodium hydroxide is a strong alkali. Ammonia is a weak alkali. Okay. Now, let's just quickly end off. So the common alkalis in your lab, sodium hydroxide, potassium hydroxide. Generally, these two are considered strong alkalis. So both sodium and potassium hydroxides are strong alkalis. They dissociate and ionize completely and irreversibly in water. Calcium hydroxide is the next one, CaOH2. Now, calcium hydroxide is a bit on the boundary. Calcium hydroxide is somewhere in between strong and weak. All right. So these are the common alkalis. And finally, you have ammonia, which unfortunately is not here. Ammonia, okay, is NH3 bracket aqueous. This is a weak alkali. All right. So let's just revise once more. A base is just metal oxide or metal hydroxide. Doesn't care whether you need to dissolve or not. Base don't need to dissolve in water. That's fine. Can be a solid. Okay. But alkalis are more restrictive. Alkalis are bases that must dissolve in water. And when they dissolve in water, it dissociates and ionizes to give hydroxide ions, OH minus. So you see, I say hydroxide so many times, because hydroxide, OH minus, OH minus is the ion responsible for alkaline properties. If there is no OH minus, it will not be pH more than 7. If there is no OH minus, it will not turn moist red litmus paper blue. All the properties of alkalis are possible because there is hydroxide ions. Okay? So you must know the two ions are acid is H+, alkali, hydroxide, OH minus. All right? Can? So today, what did we learn? We learned about acids. Acids must dissociate and ionize when dissolved in water to produce H+ ions. So acids, H+. We also learned the concept of strength of acids and alkalis. The strength is defined in terms of the extent of dissociation. Is it complete or is it partial? Okay. We also learned how to use the acid dissociation constant Ka to compare the strengths of acids. We have learned how to balance chemical equations, for which you have homework. You need to finish quick check 3 and 4 and show me in class. All right, so you can do it today. It's good practice for Friday's lesson when we come back for Pure Chem. And finally, we ended off with what is an alkali. Alkalis must dissolve in water. When they dissolve in water, the alkalis dissociate and ionize to give hydroxide ions, because OH minus is the ion responsible for alkaline properties. All right, and with that, let me just conclude the lesson here. Let me stop the recording, then I'll answer the questions, okay? Just give me a minute.